When you're dealing with these thin lenses, you're going to have to use this formula right here. 1 over f equals 1 over do plus 1 over di. Not too bad, except when are these positive or negative? Let's find out. F is the focal length. So the focal length, when you've got a thin lens, there's a focal point on each side of the lens. The focal length is the distance from the center of the lens to one of these focal points. Which one? It doesn't actually matter, because if you want to know whether the focal length is positive or negative, all you have to look at is what type of lens you have. And in this case, we've got a convex lens, also known as a converging lens. And it turns out for these types of lenses, the focal length is always going to be positive. So if this focal length right here was, say, 8 centimeters, we would plug in positive 8 centimeters. Doesn't matter, we could have measured on this side. This side will be 8 centimeters. We still plug in positive 8 centimeters into this focal length if it is a converging or a convex lens. If you had the other type of lens, here's the other kind. This one is either diverging or it's going to be concave. So if you have a concave or diverging lens, it also will have 2 focal points typically drawn on either side. These will be a certain distance along that principal axis to the center of the lens, and if you measured this, by definition, for a concave or a diverging lens, the focal length is always going to be a negative focal length. So if this distance here was 8 centimeters, you'd have to plug in negative 8 centimeters up here into the focal length. So all you need to look at is what type of lens you have. DO, DI doesn't matter. DO and DI could be big, small, positive, negative. You could have a real image, a virtual image. It doesn't matter. All you have to look at is what type of lens you have. That will tell you whether you should plug in a positive focal length or a negative focal length. All right, so focal length isn't too bad. How about DO? DO represents the object distance. So if I had an object over here, and we always draw objects as arrows, that lets us know whether they're right side up or upside down. Here's my object. The object distance refers to the distance from, always measured from the center of the lens to where the thing is, and in this case the thing is the object. So here's my DO. This object distance, this one's even easier. Object distance, just always positive. So my object distance, I'm just always going to make that positive. So if this is 30 centimeters, I'm plugging in positive 30 centimeters over there. If it's 40 centimeters, positive 40 centimeters. Always going to be positive, unless there is one exception. If you had multiple lenses, it's possible you might have to deal with a negative object distance. But if you're dealing with a single lens, whether it's concave or convex, I don't care what kind of lens it is. If it's a single lens, your object distance is going to be a positive distance if you only have one lens. Okay, so object distance is even easier. Always positive, no matter what the case is, if you have a single lens. How about image distance? Image distance is the tricky one. So this refers to the distance from the lens to where the image is, but your image can be on one side or the other. And so let's see here. Let's say for this case over here, I ended up with an image upside down over here. Something like this. Say this is my image that was formed by this object and this converging convex lens. Well, image distance is defined to be from the center of the lens to where my image is, always measured parallel to this principal axis. Sometimes people get confused. They think, well, am I supposed to measure from the center here on this like diagonal line? No, you never do that. You always go from the center, parallel to the principal axis, to where the image is. This is defined to be the image distance. When will this be positive and negative? Here's the tricky one, so be careful. Image distance will be positive if the image distance is on this other side of the lens than the object. So one way to remember it is image distance will be positive if it's on the opposite side of the lens as the object. Or, the way I like to remember it, if you're using this lens right, you should be looking, your eye should be looking through the lens at the object. putting your eye over here does no good at all, really. I mean, your lens is kind of pointless now. If my eye's over here, I'm looking at my object, and I'm just holding a lens in front of it. This is really doing no good, so I don't want my eye over there. And this, if I'm using this lens right, my eye would be over on this side, and I'd be looking at this object. I'd be looking through. I'm not shooting light rays out of my eyes, but I'm looking in this direction through the lens at my object. I wouldn't see the object. What I'd actually see is an image of the object. I'd see this image right here, but still I'm trying to look through the lens. And a way to remember if the image distance is positive, if this image distance has been brought closer to your eye than the object was, if it's on the side of this lens that your eye is on, that will be a positive image distance. So if it's on this, in this case, the right side, but what's important is it's on the opposite side of the object and the same side as your eye, that's when image distance will be positive. If you ended up, and that'll be true regardless, whether you've got concave, convex, converging, diverging, if the image is on the same side as your eye over here, then it should be a positive image distance. Now for this diverging case, maybe the image ended up over here somewhere. I'm going to draw an image over here. So again, image distance from the lens, center of the lens, to where your image is. So I'm going to draw that line. This would be my image distance. In this case, look at my eye still should be on this side. My eye's on this side because I should be looking through my lens at my object. I'm looking through the lens at the object. I'd see this image because this image is on the opposite side of the lens as my eye, or another way to think about it, it's on the same side as the object. This would be a negative image distance. I'd have to plug in a negative number, or if I got a negative number out of this formula for DI, I would know that that image is formed on the opposite side of the lens as my eye. So those are the sign conventions for using this thin lens formula. But notice something, this formula is only giving you these horizontal distances. It tells you nothing about how tall the image should be or how tall the object is. It only tells you these horizontal distances. To know about the height, you'd have to use a different formula. That other formula was this magnification formula, and it said the magnification, M, equals negative the image distance. If you took the image distance and then divided by the object distance, you'd get the magnification. And so we notice something. We notice something important here. Look at, if the image distance comes out negative, we'd have magnification is negative of another negative number. Object distance always positive. So we'd have a negative of a negative. That'd give us a positive. If our image distance comes out negative like it did down here, well, then we get a positive magnification, and positive magnification means you've got a right side up image if it's positive. And if our image distance came out to be positive, like on this side, if we had a positive image distance, well, we'd have a negative of a positive number. That would give us a negative magnification. That means it's upside down. So it's important to note, if our image distance comes out negative, negative image distance means not inverted, and positive image distance means that it is inverted from whatever it was originally. Okay, so let's look at a few examples. So say you got this example. It said find the image distance, and it just gave you this diagram. Well, we're going to have to use this thin lens formula. So we'll have to figure out what F is. F's the focal length. We've got these two focal lengths here, 8 centimeters on both sides. Should I make it a positive 8 centimeters or a negative 8 centimeters? Remember, the rule is that you just look at what type of lens you have. In this case, I have a concave lens, or another way of saying that is a diverging lens. And because I have that type of lens, it doesn't matter. I don't have to look at anything else. I automatically know my focal length is going to be 1 over negative 8 centimeters. Okay, so 1 over negative 8 centimeters equals 1 over the object distance. Here we go, object over here, 24 centimeters away. Should I make it positive or negative? I've only got one lens here. That means object distance is always going to be positive. So that's 1 over positive 24 centimeters. Now we can solve for our image distance. So 1 over DI. If I use algebra to solve here, I'll have 1 over negative 8 centimeters minus 1 over 24 centimeters. And note, I can put this all in terms of centimeters. I could put it all in terms of meters. It doesn't matter what units I use here. Those are the units I'll get out. I just have to make sure I'm consistent. Okay, so if I solve this on the left-hand side, turns out you'll get negative 1 over 6 centimeters equals, well, that's not what DI equals, that's what 1 over DI equals. So don't forget, at the very end, you have to take 1 over both sides. So if I take 1 over both sides, my DI turns out to be negative 6 centimeters. What does that mean? DI of negative 6 centimeters. Well, that means my image is going to be 6 centimeters away from the lens, and the negative means it's going to be on the opposite side as my eye or the same side as my object. So my eye is going to be over here. If I'm using this lens right, I've got my eye right here looking for the image, and a negative image distance means it's going to be over on the left-hand side, where 6 means 6 centimeters, and away from what? Everything's measured from the center of the lens. And so from here to there would be 6 centimeters. So this tells me on my principal axis, my image is going to be right around here, 6 centimeters away from the lens. But it doesn't tell me, no, this does not tell me how high the image is going to be, how tall, whether it's right side up. Oh, actually, hold on. It does tell us whether it's right side up. This came out to be negative. Remember our rule? Negative image distances means it's got to be right side up. I'm going to have a right side up image, but I don't know how tall yet. I'm going to have to use the magnification equation to figure that out. So I'll come over to here. Magnification is negative DI over DO. Well, what was my DI? So negative of DI was negative 6. So I'm going to plug in negative 6 centimeters. And on the bottom, I'm going to plug in, let's see, it was 24 centimeters was my object distance. What does that give me? Negative cancels the negative. I get positive, and I get positive 1/4. Positive 1/4. And remember here, positive magnification means right side up. 1/4 means that my image is going to be 1/4 the size of my object. So if my object were, say, 8 centimeters tall, my image would only be 2 centimeters tall. And so I'm going to draw, I've got to draw an image here that's right side up because I got a positive, and it's got to be 1/4 as big as my object. So let's see, 1/4 might be around here, so it's got to be right side up and about 1/4 as big. I'd get a really little image. It'd be right around there. That's what I would see when I look through this lens. So that's an example of using the thin lens equation and the magnification equation.